Hello everyone, this is lecture number 3 on boundary value problems. Today I will discuss about a one-dimensional wave equation, its solution, how to simplify its solution when the initial velocity is 0, and numerical problem based on the wave equation. The solution of a one-dimensional wave equation is given by equation number 18. uxt summation over n from 1 to infinity capital Bn cos of lambda nt plus capital Bn star sine of lambda nt into sine of n pi over L into x. With these coefficients Bn and Bn star, they are given by equation number 21 and 24. Capital Bn is 2 by L 0 to L integration f of x sine n pi over Lx dx, and Bn star is given by 2 upon nc pi integration from 0 to L g of x sine n pi over Lx dx, equation number 24. In equation number 21, fx is the initial deflection of the string, and in equation number 24, gx is the initial velocity of the string. So equation number 18, 21 and 24, this is a complete solution of one-dimensional wave equation as we discussed in lecture number 2. Now we simplify the solution given by equation number 18, that if initial velocity is 0, then what will be the deflection in the string at any time t at any point x. If the initial velocity is 0, it means gx is 0. So from the equation Bn star, which is equal to 2 upon nc pi integration from 0 to L g of x sine n pi over Lx dx, this is 0. So from equation number 18, we have capital Bn star is 0. So the deflection uxt, this is given by, see the box on the slide, summation over n 1 to infinity capital Bn cos of lambda nt sine of n pi over Lx, and capital Bn is given by this formula. Now see this expression which I have marked as star. We will simplify this formula expression and we get this expression in terms of initial deflection, that is function f with slight modifications. Here we will use the formula of sine a cos b. It is equal to half sine of a plus b plus sine of a minus b. Now I am using the deflection formula for the case when initial velocity is 0. In the summation expression, we have cos of lambda n in t into sine of n pi over L x, and the formula for lambda n is nc pi upon L. So I'm just putting the value of lambda n. So the expression with the summation term, we have cos of lambda nt sine n pi over Lx, put the value of lambda n and now apply the above formula sine a cos b. So this expression sine n pi over Lx into cos of nc pi upon L into t, it is given by half sine of n pi over L, we can take common, and the first argument with the sine term is x minus ct plus sine of a plus b. So it is now n pi upon L x plus ct. It's easy to write this formula. Now using this formula, from equation number 18, now we can rewrite the deflection u as half, I am taking common, summation over n 1 to infinity keep the constant capital Bn as it is, and now just put the value of cos lambda nt sine n pi over Lx as discussed above. So we have with constant Bn, we have now sine n pi over L into x minus ct plus sine of n pi over L x plus ct. See the expression I have marked as star. Now separate these two terms. So I'm just rewriting it. uxt is half summation over n1 to infinity bn, then the term with sine n pi over L x minus ct plus summation over n1 to infinity bn sine n pi over L x minus ct, which I am denoting as equation number 25. Now we further simplify this equation number 25. Here I am rewriting equation number 25. uxt as half first term summation over n1 to infinity bn sine n pi over L into x minus ct. I have underlined this expression x minus ct plus summation over n1 to infinity bn sine n pi over L into x plus ct. And the expression in this second summation term with sign is x plus ct. So I am calling this one as 1 and 2. Now to simplify this expression 25, first term and the second one, we will use the calculation of Bn. In lecture 2, we discussed about the solution of one-dimensional wave equation satisfying initial conditions, and for that we used half-range expansions. So I am recalling equation number 19 from lecture number 2. Please refer to lecture number 2 for this equation. While calculating Bn using the initial deflection, we got equation number 19. F of x, that is the initial deflection at time t equal to 0. This is equal to summation over n 1 to infinity bn sine n pi over L into x. In expression 19, I have underlined the argument x with the sign term as star, and on the left side of equation number 19, we have f of x. Now using equation number 19, we can calculate equation number 25, first summation term and the second summation term. We can compare the second term and equation number 19, second term in equation number 25 and equation number 19. If we see these two expressions, then summation n1 to infinity bn sine. In equation number 19, we have sine n pi over L x. Then using equation number 19, this is f of x. Now see carefully the second expression in summation term in equation number 25. We have summation over n 1 to infinity bn sine n pi over L, and we have now x plus ct. So comparing expression number 2, and I am calling expression on the right hand side of equation number 19 as 3. So now we compare 2 and 3 from equation number 25 and 19. We can say that f star x plus ct, or you can simply write down even f of x plus ct also. This is equal to summation over n 1 to infinity bn sine of n pi over L x plus ct, and that is equation number 26. Or we can simply say that in equation number 19, replace x by x plus ct. Then the right hand side of equation number 19, this is the same expression as second summation term in equation number 25. So the second expression in equation number 25 reduces to f of x plus ct. Similarly, in equation number 19, replace x by x minus ct. We will get first expression in the summation part in equation number 25. See the right hand side of equation number 27, and using equation number 19, this will be equal to f of x minus ct. So finally, using equation number 19, we can find out expression number 1 and 2 in equation number 25 as f of x plus ct and f of x minus ct. So finally 25, 26 and 27, these equations imply that uxt is given by 1 by 2 f star x minus ct plus f star x plus ct. That is the final equation number 28. So finally, the deflection in the string when initial velocity is 0 is given by equation number 28, where this f star is the odd periodic extension of the function f of x with period 2l. So equation number 25 is now very much simplified form of solution of one-dimensional wave equation for the case when initial velocity is 0, and just by using the initial deflection we can find out the position or the deflection in the string at any point x at any time t. Now the initial deflection f of x is continuous on the interval 0 to L, and it is 0 at the end points. So it follows from equation number 28 that deflection is a continuous function of both variables x and t for all values of these variables. Now we discuss about the physical interpretation of the solution given by equation number 28. I am just writing here equation number 28 that the deflection in the string uxt for the case when initial velocity is 0 is given by 1 by 2 times f star x minus ct plus f star x plus ct. C is greater than 0. Now before starting the explanation of equation number 29, let's discuss about the shifting of graphs. Suppose function f of x is given to us, and consider figure 1 here. Suppose this is the graph of the function f of x defined from 0 to L. Now f star is just the extension of this function, so I'm just in fact it is an odd periodic extension, so I'm just extending this on the left side as an odd periodic function. Now given function f of x and its graph, we would like to find out the graph of f of x minus ct and f of x plus ct. Now to find out the graph of f of x minus ct, we just pick the graph of function f of x and shift it in the forward direction by a distance ct. See figure 2 here on the slide. So as it is, we pick the graph and shift it in the forward direction. Similarly, the graph of f of x plus ct is obtained by f of x graph. In this case, we shift the graph as it is in the backward direction by a distance ct. See figure 3 on this slide. Now equation number 28 tells us that the deflection in the string at any point x at any time t, it can be obtained just by using the initial deflection f of x for any given value of time t and constant c. Then we just shift the graph, that is the initial deflection, in the forward direction by the amount ct, and in the backward direction again by the same amount ct, and then we take the average of these two new graphs over the interval 0 to L. Whatever is the average of these two functions, that is the deflection in the string at any time t. Here I am just concluding the result that the graph of f star x minus ct is obtained from the graph of f star, that is the initial diffraction, by shifting the graph of f star x by ct units to the right. This means that the f star x minus ct, it represents a wave that is traveling to the right as t increases. Similarly, f star x plus ct represents a wave that is traveling to the left, and uxt is a superposition of these two waves. Consider the numerical problem. We have to find out the solution of a one-dimensional wave equation corresponding to the triangular initial deflection f of x. It is given as 2k upon L into x for x between 0 to L by 2, and 2k upon L into L minus x if x lies between L by 2 to L. So this is triangular deflection, and given that the initial velocity is 0. From lecture number 2, we can recall equation number 1, 2 and 3. The deflection uxt is given by summation over n 1 to infinity bn cos of lambda n t plus bn star sine of lambda n t into sine n pi over L x, with the coefficients bn is given by equation number 2, that is 2 by L integration from 0 to capital L f of x sine n pi over Lx dx, and bn star is given by 1 upon nc pi integration from 0 to L g of x sine of n pi over Lx dx, that is equation number 3. Now gx is the initial velocity, and here initial velocity is 0, so this implies that coefficient bn star is 0 for all values of n. So in this case we have to just calculate the formula for bn. Now calculation of bn is almost similar to the numerical problems for Fourier series. Put the value of f of x. So for this we break the integral into two parts, 0 to capital L by 2, and then second one is L by 2 to L. Now I have marked different functions here as 1, 2, and similarly in the second integral also. And now we integrate these expressions, and we will integrate by parts. First function I am taking as x, and second function is sine n pi over Lx. I am not discussing the details of the calculations here. Integration part is easy, so we will integrate twice, and finally we get the values. See the last expression here. After integrating and putting the limits, we have something like this. We have two terms with cos of n pi by 2, second last line here, plus the second expression 1 upon n pi over L whole square sine of n pi over Lx. Now we have to put the limits here 0 and L by 2. Now when we put the limit in the sine expression, everything will be simplified. In the second integral term, we again get an expression something like cos n pi by 2. So these two expressions which I have underlined, they will cancel out, and we just have this sine expressions. On simplification, bn is given by 8k upon n square pi square sine of n pi by 2. Now this expression sine n pi by 2 can be further simplified. For n even values, this expression sine is always 0. So only for odd values of n, we will get some non-zero values. So bn is 0 if n is even, and if n is odd like 1, 2, 3, we have alternatively positive and negative signs. So if you want to keep this expression as it is, you can keep it, or you can simplify it further. Let n is 2m minus 1, where m is taking values 1, 2, 3 and so on. So Bn is given by 8k upon n square pi square minus 1 raised to power m. Now just put the value of Bn in equation number 1. We get the formula for deflection of the string. You can leave your solution here also, or you can simplify it further for n equal to 1, 2 and so on. Now we will find out the deflection in the string, but not mathematically but geometrically. For this we will use the solution of the one-dimensional wave equation for the case when initial velocity is 0. In that case, the solution of the one-dimensional wave equation is given by uxt, which is equal to half average of f star x plus ct plus f star x minus ct, where this f star, this is the odd periodic expansion or the initial deflection. So here the initial deflection given in the numerical problem is triangular. We can draw its graph. It is given by figure 0, the first figure here, 0 to L, and the function f of x is given as this triangular shape. Now at time t equal to 0, the initial deflection of the string is same, that is figure 0. Now I'm just using this expression and finding it by the above formula, that is the average of initial deflection f star x plus ct and f star x minus ct. Now figure 1, this is the graph of f star x. Here I am taking t as 0. So suppose time t is 0. Then I am plotting the graph of 1 by 2 f star x in figure 1. As t is 0, so f star x plus ct and f star x minus ct both will be same. So I am writing two things here, one with the black pen and other one is with red curve, you can see. So this is half of the deflection. See the figure 0 here? I have reduced the size of the graph by half at every point. So we have k by 2, maximum length is at the height is at the point L by 2 and it's capital K by 2. So in that case, the deflection in the string is given by 1 by 2 times f star x plus f star x, because that ct part is 0 and this is exactly same as f star x. This is obvious case, still I discussed it so that you can have idea. Now let's move to the next case. Now we find the deflection in the string at a time t equal to L by 5c. The deflection ux comma t is given by half f star x plus L by 5 plus f star x minus L by 5. Now in this equation, the first function is obtained by shifting the graph of initial deflection f star x in the backward direction by L by 5 units. And the second function f star x minus L by 5, its graph is obtained from the graph of f star x by shifting it in the forward direction by L by 5 units. So in figure 1, I am drawing the graph of f star x and the remaining these two functions by shifting forward and backward. In figure 1, the dotted graph, the triangular shape, is the graph of half f star x. Now to find the graph of f star x plus L by 5, we shift this triangular graph in the backward direction by the units of L by 5. So you can see the red graph, and this is the graph of half f star x plus L by 5. You can extend this on the left hand side and the right hand side as an odd periodic expansion of this function. Now to find the graph of f star x minus L by 5, we shift the graph, the dotted triangular graph, in the forward direction by L by 5 units. You can see this thing here. Now the deflection in the string uxt is given by the superposition of these two graphs. So first go to figure number 3. Now in this figure I am just drawing the graph of these two shifted graphs, half f star x plus L by 5 by red curve and f star half of f star x minus L by 5 by the black curve. Now we just add these two curves and we get the deflection in the string, which is given by figure number 2. See carefully, at x equal to 0 the graph of red, it is exactly same above the x-axis as the black curve below x-axis. So when we add these two, value is 0. Similarly at x equal to L, one is positive, another one is negative by the same amount. So again at L, deflection is 0. So you can see in figure 2, at x equal to 0 and x equal to L, the deflection is 0. Rest we just add these two graphs and finally we have figure 2 as the deflection in the string at time t equal to L by 5c. Similarly, we can take different values of time and just by superposition of these two shifted graphs, we can find out the deflection in the string. Try these numerical problems. You have to find out the deflection in the string of length L equal to 1, c square equal to 1, initial velocity is 0 and initial deflection is given by f of x. So there are three numerical problems. Here we are assuming that k is small. So for these three problems, you have to find out the deflection. So in that case, bn star is going to be 0, and as discussed in the previous numerical problem, you have to just find out what is bn.